Hello everyone. This video is about controlling DC motor that consumes a lot of electrical power. Actually so much that one MOSFET transistor wasn't enough. I have tested that. So this motor is actually inside an oil pump. It's rated 12 volts, 5 amps nominal, but when it is starting, it takes slightly over 10 amps, kind of surge to win mechanical friction. Of course, that accelerating of motor and whatever load the pump is, and the circuit is such that it must be isolated. Otherwise, we would burn components from microcontroller board. I have used 4N35 optocoupler, and it is really important design principle that you separate concerns when you design power consuming parts. You can kind of cover this part and concentrate doing things that this should perform. This isolation gives us the luxury that when I cover this part, I can concentrate on like software in this microcontroller board and user interface on a breadboard that is tied to the software. And even then, I should have separate power supply for the breadboard so that ensures stability of software execution. Uh, 0.5 amps from the USB port really can't provide anything else than this TTL level. That's 5 volts output from these ports, like 20 milliamps max. So yeah, you can blink one or two LEDs, but still you should have this separate power supply. For example, rechargeable AA size batteries, 4 of them. In real life, that sums up to 5.1 or 5.2 volts when they are fully charged, and some 4.9 volts when they are depleted and you should recharge. Power supplies are really a separate concern on their own. Now I have decided that because I had a battery pack from a dead laptop, and those cells inside the battery pack are 12 volts nominal value, and when fully charged, multimeter shows like 40, yeah, 14 volts. If this was kind of automotive application, then this high current power supply would be car battery, and it behaves quite much alike. I like this laptop battery, but of course, car battery comes with a lot more capacity that you can pull from. This is fully isolated. There's no common ground for this part and this part. That was the design goal. And software gives pulse width modulation to this optocoupler. There's LED inside. You can read from datasheet. And then there's photosensitive transistor inside. I think that's about it. I will not go into physics, but because there is LED inside, you must take care that you limit the current so that you don't burn that LED. And then for this application, I wanted to have 0.1 microfarad polymer cap so that I get slightly longer lasting pulses of light, because I'm driving motor. That's my motivation. And here, because I have power transistors and they are fixed to an old CPU cooler, that's a practical way to reuse those old coolers that really don't fit anything more modern, more fat for the fan. And I must take care that this fan does not get too much power. So there's 6.7 ohm resistor and one rectifying diode, this 1N 4007. So there's current limiting and kind of voltage drop, so that fan doesn't go as fast as it can. With too much current, it could self-destruct too early. Pulses are treated with 500K pull-up resistor, and there's 10K pull-down resistor. Most FETs are so voltage sensitive that you don't want to have them floating. You do not want to experience undefined voltages to this load. And because it is inductive load, we must have a diode that can take several hundreds of volts, clamping that inductive feedback so that doesn't destroy our transistors. On datasheet, this can take 100 volts maximum range of source. And there's some second version that is 7 amps only. Components can't take just anything, but I think it is interesting to demonstrate and to see what this can do. So I will hook up the battery. That is cooling fan making noise. There you can see so-called motor poles, but I'm not gonna pump any engine oil or diesel fuel or so. That's messy business. Let's skip that. This is reusable for other purposes. How about 100-watt LED module? That takes a lot of current as well. If you want to dim that 100-watt LED module, sure, then this is somehow meaningful. Those plastic battery holders, they are economical. Go get one. And at the moment, the part is zeroed. Gate is experiencing only 0.22 volts. It doesn't do quite anything. But of course, this is dependent on used transistors, and you need datasheet to confirm. Now I'm turning that potentiometer slowly. That sound comes from the motor coil. That was enough to win all kinds of friction resistance. Now I have a little bit fine tuned with push button switches. When the motor is running and that pump is being operated, it requires less energy than the startup. This is kind of proof of it. Yeah. Now back to this potentiometer. Now this number here is only approximation. What pulse width modulation duty cycle would average. So 0% duty cycle is 0 volts, 100% duty cycle is 5 volts. That is Arduino specific. And remember, here we have multimeter interpretation. What gate is experiencing, that's volts. This is the maximum. The motor is still running. After this short demonstration run, this whatever aluminum alloy heatsink feels like the room temperature. It's not hotter, it's not colder. It's cooling works. I think that's about it. We did hopefully learn something